In this video, we're going to implement a transformer emulator or operator architecture in JAX to emulate the one-dimensional advection equation. We will discuss the decoder-only part of the original Attention is All You Need paper and then implement all its parts in great detail. We will start with the dot product attention and multi-head attention. We'll discuss how to split attention across heads. We will implement a transformer blocks with corresponding vectorization over the individual axes. We're going to implement a positional encoding. We will describe the transformer architecture. We will wrap this into a format that can be used with physics states. And then eventually we're going to use the APEBench benchmark suite and include the transformer and compare its performance against the feed-forward convolution network and run a very simple study on Colab and then post-process a training loss convergence, a metric rollout, and some sample trajectories from the emulators. Let's get started. The channel sponsor Pasteur Labs is currently hiring SciML and software engineering positions. Check out pasteurlabs.ai/careers for more details. Hi and welcome to this new video in which we will implement a transformer architecture in JAX using Equinox to approximate the time-stepping behavior of the advection equation. So we will train the network to take in one frame or one state of the advection state space and then produce the next state in time. Then we can auto-regressively roll out this emulator to produce a trajectory. We will implement the architecture in great detail, and then we will abstract the aspect of training, testing, and benchmarking using the APEBench benchmark suite in JAX. This also allows us to compare the performance of the transformer against other architectures like simple feed-forward convolutional networks. For simplicity, we will work in 1D and we will use periodic boundary conditions, which is a requirement to use APEBench. There are, of course, multiple variations of transformer architectures. Here we will try to follow the original Attention is All You Need paper by Vaswani et al. From 2017 as closely as possible. Specifically, we will implement a decoder-only structure, which means there will be no encoder part, which you would typically find in language translation tasks, but rather we only have this decoder part of the transformer. And this architecture structure is also what you currently find in these generative AI models, aka the large language models like ChatGPT and so on. How does that look like? Of course, we will modify a bit because here we will not work on applying an attention mechanism over time, but rather we want the attention mechanism over space. And of course, we also have a bit of a different setup. So here I took this schematic from Vaswani et al. And rotated it here. And essentially what we see is the transformer layout. In the beginning, we will lift our physics state. So we will have some physics representation, usually by having nodal values of our discretization. And then we will lift it from the one-dimensional state space, or not one-dimensional state space, but one-dimensional channel space in which the solution to the advection equation lives into a higher dimensional latent space. This is the first part here. Then we will apply some positional encoding because within the transformer, we're going to attend over the spatial discretization points. And by a vanilla version of a transformer, the attention mechanism would be permutation invariant. So that means it does not have a sense of position. And so we will add a very simple sinusoidal positional encoding, which was also done in the Vaswani paper, to inform each channel and each spatial positions of its respective channel and positional index. And then a transformer essentially consists of multiple transformer blocks being stacked sequentially. And here we will use the layout again from the Vaswani paper, where we will first compute a multi-head attention, but here as said, we will attend over space. And after the attention, we are going to add a residual stream and apply a normalization layer. And then the second step is a feed-forward multi-layer perceptron, which is vectorized over the spatial axis and only applies in this hidden channel axis. And then ultimately we'll also have a residual stream that's going to be added and a normalization layer. In the middle here, you would find arrows coming in from an encoder structure. And as said, we will have a decoder-only structure, which means this part will not be part of our transformer block. And also one point, since we have the attention over space, we do not have this temporal consistency for which you would usually use a masked attention. You would mask your attention results such that current tokens cannot affect future tokens, or past tokens cannot affect future tokens. But here in our spatial attention mechanism, we do not have to care about this because our spatial range would always be the same, and we do want that all spatial point can attend to all other spatial points. Our transformer then essentially ends not in producing probabilities over a dictionary of tokens, which is what a typical transformer in a language task would do, but rather we will project down the higher dimensional latent space into a state which is again compatible with the physics state that we have here. So in order to implement this in JAX using Equinox, we need to implement the following components. We need a scaled dot product attention mechanism, which is going to be part of the attention layer. Then we need to find a way to implement the multi-head attention, which is essentially a clever way to vectorize over individual attention heads. Then we're going to wrap a multi-head attention, the residual streams, the normalization layers, and the multi-layer perceptrons into a transformer block. So this is essentially what you see here in this light gray area. And then we're going to stack multiple transformer blocks into the transformer architecture. We need to implement the positional encoding. And then ultimately we need this interface between the terminology of these physics emulation, which is very close to what you see when applying ConvNets and when you work on image data. And we need to translate this terminology into this what you typically find within the transformer world. Once again, we will not implement the attention mechanism with a masking because we attend over the entire space and we do not have an attention over time. The emulator behaves auto-regressively such that it takes a state, predicts the next state in time, and then feeds on its own output. During training, we will use the simplest setup for this, which is a one-step supervised training setup where it just trains to predict one step into the future, but then during testing, we will have it predict a longer trajectory, I think 100 or 200 autoregressive steps. And I think one last thing to note here is that we were gonna make heavy usage of the automatic vectorization in JAX, which I believe is a very nice way to implement transformer architectures because it allows us to keep it closer to the mathematical description and not worry about batch axes. Because as we will see later, during the transformer architecture, we will batch multiple times, but oftentimes over different axes. And with the automatic vectorization, we can automatically determine or manually set basically over which axis we want to vectorize. Okay, very nice. Then let's start with the coding. So here I already prepared the imports. So we're going to use some typing variables that's relevant for later on defining the architectures. We will import Equinox, which is a deep learning framework in JAX. Of course, we need JAX itself. We need the NumPy interface to JAX. And I'm also using JAX typing as type annotations that will help us to more precisely tell what kind of shapes the arrays are made of and also give the respective axes some names. And I think this makes it more intuitive. Then as mentioned, we will use APEBench to train and test our transformer. So we're going to import this. We will use Seaborn for the statistical plotting because with APEBench we will then run a statistical experiment over multiple seeds, and with Seaborn we can nicely aggregate over different random seeds, and then just matplotlib to further modify the plots. Before we start coding the transformer architecture, I first want to take a look quickly at how this data related to the advection equation looks like. For this I want to instantiate an advection scenario from APEBench. So we will say APEBench.scenarios.difficulty.advection and then just instantiate this class. We thereby also use its default settings. If you want to learn more about APEBench, I have a video linked up here where we'll also use the difficulty-based advection scenario. And then we can use an APEBench scenario to extract training data. So let's call this the train data, and this is advection scenario.get train data. Let's see if the autocomplete works. And let's take a look at the shape. So basically this is going to be a JAX array, and this JAX array should tell us its shape exactly. So here it's a 4-axis array. In the last axis, it has 160, which refers to the spatial discretization points. Then it has a channel axis. Here in one-dimensional advection, there is only one channel, which is the advected quantity. And then we have 2 more axes. This axis, per definition, is a temporal axis. So we basically have a sequence of 51 snapshots. And then we have an sample axis, so we have 50 different trajectories. Let's take a look at what this trajectory looks like. So we can plot 2 subsequent states by taking train data, indexing it as 0, so taking the 0th trajectory, and then we make :2 to plot the first 2 frames. And then I will extract the 0th channel axis using a colon, and then using a 0, and then I will use a colon over the spatial axis. And then in order to plot 2 lines at the same time, I have to transpose this to have the batch axis for plotting last. And then essentially we will get this. So in blue, we have the frame earlier in time, and in orange, we have the frame later in time. And you see that the advection equation is moving a state through time. So here on the x-axis, we have our spatial points, and then everything is moved to the right. If I were to add another state, so up to :3, you would see that this process just continues. By itself, the advection equation is a very simple physics phenomenon. And of course, you then have multiple trajectories. So we could, for instance, access trajectory 1, which would look a bit different. And I think you now get an idea of what this data is made of. And what we now want to do with our transformer is to have it learn to predict from the blue frame or from the blue state to the orange state. So given the blue state, predict the orange state while attending over space. So use the spatial axis as the axis over which you intend. Very nice. With this out of the way, we will look at it in more detail later during the benchmarking. We can start the implementation. And let's start by implementing the scaled dot product attention. So here I copied the formula that is taken from the original Vaswani et al. Paper. And an attention mechanism requires us hand over a query, a key, and a value array, and then compute an attention output as taking a product between the query and the key, scaling this, applying the softmax, and then multiplying it with a value. So let's implement this, and let's call this the scaled dot product attention. Like in the mathematical formula, it will take in a query. And now we will make usage of the JAX typing to inform what kind of shape this is made of. So this is going to be a float array, which has 2 axes. And the first axis is going to be the sequence length. In the beginning now, we will still speak in the terminology of language modeling or this sequential modeling of tokens. So its first axis or 0th axis is going to be the sequential length. And then we will have a key size. So this is basically a channel dimension or a feature dimension. So for each entry in the sequence, we basically have a corresponding vector of this key size. Then we have the key, which is another floating point or float point value array with the sequence length and the key size. And then we have the value, which is another floating point array with the sequence length and a value size. And then the attention should return another floating array with the sequence length and the value size. And just to make sure that here we don't do any masking order, that is clear, we will add a small docstring and say no masking. And then the first thing to do is to extract this dk here, which refers to the size of the query or the key, which is used as a scaling factor within the softmax in order to ensure that the logits that are computed are somewhat reasonable. So we can either extract it from the query or from the key. Let's just use the query, and then let's call this the key size is going to be query.shape at -1. And then we can compute the quantity within the softmax, which I want to call the attention logits. So logits is typically a name you use for the quantities before you apply the softmax. A softmax would take values within a vector and ensure that these values within the vector can range from -infinity to +infinity, and it would then map them to probability values. And these values, before they become probability values, are typically called logits. And here, in order to compute them, we will follow the formula. So we will take the query and matrix multiply it, so I'm using the add here, with the transposed key. And let's take a look at what happens. So we take the query, which is of sequence length times key size. Then we have the key, which is of sequence length times key size. If we transpose it, it's going to be of key size times sequence length. And then we make a matrix multiplication over the key size. So the key size is going to be contracted, and we're left with a tensor which will have, let's make a float array and say this is essentially sequence length to sequence length. And to also include this here, let's add the normalization with jnp.square root of the key size. And here what we essentially get is a matrix which is quadratic in the sequence length. And this is also typically the computational bottlenecks that you see in big transformer architectures, that you have a quadratic complexity with regards to your context size, or with regards to the number of tokens that are in there. And here in our case, since we will then later on map the sequence length to the spatial size, which here is 160, this attention logits matrix is going to be 160 by 160. Still reasonable, but of course you can imagine if you had large discretizations, that would get very large. And you do, of course, have to somehow store this respective results, but you also have the quadratic complexity with regards to these computation here. Okay, anyway, but let's use the attention logits to apply the softmax to it. Then we essentially get attention weights, or you might call them attention probabilities. But maybe before we do that, let's take a quick look at what is happening here conceptually. So what we essentially do is we have a query and a key, and essentially we map we contract over the respective feature axis, so here the key size, and then we essentially know how each entrance in the sequence, or in our case, how each point in our space wants to attend to another point in space. So for instance, if we took the matrix and indexed it at row 20, column 140, we would see how does the value, or the blue value at position 20, or what does it want to attend to the value at 140. So what does this value want to know from the value later on? This is again in this logit format. Then we will want to max it, or want to map it into the probability format, because then we essentially have a weighting, and then we know if there's a high probability of the relation from 20 to 140, we know that this is this relation between these two spatial points is of high importance, and is then going to be used when contracting against the value array. Okay, but long story short, let's implement the float array, and this will of course not change its shape, so it will still be sequence length by sequence length, and it's going to be found by applying jax.neural-network.softmax on the attention logits, and it will map over the last axis. So the first axis, which is of length, sequence length, is basically at which token am I, and the column axis, or the axis thereafter, is basically to which token or to which entry in the sequence I want to attend. And of course, we want to softmax the logits over this letter axis. And so we will use axis -1 to index the last axis, so basically from the rear. Okay, and then we basically have concluded this softmax and the bracket. And essentially in the last part is going to be to define the results. And let's first perform the computation and then add the typing. And we will say attention weights matrix multiplied with the value array. And now let's take a look. So basically we have a sequence length by sequence length matrix multiplied with a sequence length by value size matrix. So the result is going to be, again, a floating point tensor with sequence length by value size, because we will contract over sequence length or over axes of length sequence length. And this is also the shape we want to return. So we will just return the results. This is our simple scaled dot product attention. Our next step is to use this scaled dot product attention mechanism to implement a multi-head attention layer. And for this, I will copy in its mathematical description. So now what we want to produce is essentially this part here. And how does it work? So it takes the current state of the sequence, so in the transformer terminology, which consists of an axis over the sequence length and then a feature axis or a hidden channel axis associated with each token in the sequence. And let us call this input X. And then we need to do two things. So we need to project X into query, a key, and a value. So we need to project this hidden channel axis into the query or key size axis of the query, into the key size axis of the key, and into the value size axis of the value. And for this, we're going to use a linear mapping with a learnable matrix, or the learnable weights of a matrix. So here they are denoted as WQ, as WK, and as WV. And then essentially we want to project down the result of the attention mechanism back into the hidden channel space or this feature space. So we also need an output matrix here called WO. So this is one part of what this layer is going to do. But then most importantly, it's going to do multi-head attention. So what does that mean? So we could very well do the attention over the query, key, and value tensors we would get after the mapping in the respective channel space. But the point is that we oftentimes want to use an attention over a smaller subset of this projected axis. And the reason is, usually in a language modeling task, you could say that a token at a specific point in a sequence can attend to another token, not just once, but can basically ask different questions. So we can think of this attention mechanism as asking a question to another token in the sequence. And of course, there can be multiple quotation marks questions they can ask. In the context of our physics state, it's a bit more complicated to think about. But when we are within the application of an attention mechanism, we are of course not having a one-dimensional channel space. So of course here this blue axis or this blue curve only has a one-dimensional channel, but have like our hidden channel. And then of course, when we, for instance, again, attend from position 20 to position 140, we could attend for this different aspects of this hidden channel dimension or hidden channel axis. And so we are going to split the query, key, and value tensor into smaller heads and then vectorize over the heads. That sounds a bit strange if you really put it into these formal terms, but I guess the implementation starts making a lot of sense. So let's start with the implementation. And for this, we will also now start using Equinox. So let's implement a layer and call it the multi-head attention. For this, we have to subclass from Equinox module to have it become an Equinox layer. And then essentially, what do we have as attributes? So we need to save the number of heads. So the number of heads is going to be the number of attentions we do in parallel. So this is going to be an integer. Then we need a query projection. So in this term here, it is just a weight matrix, but we're going to implement it as a linear layer. So it's going to be equinox.neural-network.linear. Then we need a key projection, which is also another equinox.neural-network.linear. and we need the value projection, which is equinox.neural-network.linear, and we need an output projection, which is also equinox.neural-network.linear. Then let's first implement the constructor of this layer. This essentially takes the number of heads, which is an integer, and it requires the number of channels. So here I want to call it channel. It's a bit of an uncommon terminology you have in language modeling tasks. Here you might call it an embedding dimension. So essentially what kind of an how large this feature space is within your where your tokens reside in. But here, in order to keep it closer to physics, more closely to the physics terminology and the terminology, you have an image modeling tasks. I want to call it the number of channels. Since we are within the transformer, this is of course these hidden or latent channel access. And then to be compatible with Equinox and JAX, we need our reproducible randomness. So we need to provide explicitly a pseudo-random number key, so a PRNG key array under a keyword argument. So this is our multi-head attention. So what do? So first we need to split our random keys into 4 separate keys to instantiate the corresponding linear blocks or to initialize the matrices. So let's call this the query projection key. Then we have the key projection key. So now key repeats, but of course these are different meanings of key. Then we have the value projection key. We have the output projection key. And we get those by saying jax.random.split of key into 4 subkeys. And then we can instantiate the query projection. So query projection as equinox.neural-network.linear. And then I hope, yes, the autocomplete works. So a linear layer is defined by its input features, its output features. And so as input features, we have number of channels, and as output features, we have essentially the query size. So this is the key size especially, but for simplicity, I want to keep this the same. So this is of course a way to tune the transformer architecture that this differs, but here I will just have this the same. Then importantly, I will use bias false. So it's going to be a truly linear layer. It's not going to be linear affine. This is also in order to be closer to the implementation of Vaswani et al. Of course, there's also a way to tune this architecture, but here I will use it without a bias. So it's really just the weight matrix. And then as the key, we will provide the query projection key. And then essentially I can repeat this because the other projection operations look pretty much the same. So we then have the key projection, which uses the key projection key. We have our value projection, which uses the value projection key. And then ultimately we have our output projection, which should use the output projection key. And then as the last part, we can save the number of heads as our attribute and say self.num heads, so is num heads. So that finishes the constructor. Then we can go into its forward pass or its call signature, saying __ call, and then say self. And what do we get in? So we get the current state of the sequence. So X is going to be a floating point array filled with sequence length and channels, or you could also say number of channels. And then it processes this and returns another floating point array of sequence length and channels. So essentially what we want is that this block then represents this part of our transformer block. Let's get down again. And then let's extract the sequence length and channels from our input array. So sequence length and channels is x.shape. And here you would also wonder, in an implementation with, for instance, PyTorch, TensorFlow, or also if you use like Flex, which is also a popular deep learning framework in JAX, you would have to explicitly carry a batch access. But here with Equinox, we nicely do not have to do this because we're going to implement all our architecture single batch, so without a batch access. And then during training or when we need the architecture, we can use JAX VMap and automatically vectorize it and thereby add a batch access. Because a batch access, as its name suggests, should only batch the computations, so we don't have to worry about that. And I think this is quite relieving because here our arrays then only stay of or only 2 access arrays instead of being 3 access arrays, which typically makes the operations more complicated. First step, we need to lift or do this linear mapping. So let's do just that and say we get the query by applying self.query projection, query projection on X. But here, careful. So as said, by default, all Equinox architectures are single batch, meaning that if you instantiate a linear layer, it maps from a vector of the input num channels to a vector of the output num channels. And here, the input is not a vector. The input is a matrix. It is a 2-axis tensor. So this is our first time we will use the automatic vectorization because the projection, of course, vectorizes over the sequence length. So each sequence entry or each token is processed individually, but with the same weight matrix. So we will say jax.vmap of self.query projection applied to X. Let's add a handy comment here and say needs to vectorize over the sequence length. Similarly, we get our key. So this is not just a quick repetition, jax.vmap of self.key projection applied to X. Sorry, not to Y, but to X. And we get the value with jax.vmap of self.value projection applied to X. So now we basically have transformed our input into query keys and value. And now we will split over the last axis. We will split over the key axis or this key size or value size axis, or precisely this, since this did not change, so we split over the number of channels into the heads. I'm going to use a reshape command. So we're going to say that query is going to be query.reshape into the following shape of sequence length, then self.number of heads, and channels integer divided by self.number of heads. So essentially we turn our 2-axis array of query, which is of length, sequence length by channels, or we can maybe also add a typing annotation here, float array of sequence length, and then we have query size, which in our case is just another num channels. But here, after this modification, we now have an array which is still of sequence length. So this has not changed, but then it has num heads in an interior axis. And as the last, maybe let's move this into the next line. As the last axis, we basically get query size integer divide by num heads. So imagine, for instance, channels was 20 and the heads were 4. So we used a multi-head attention with 4 heads over a query size with query dimension 20. Then the result would, still be sequence length. This does not change, but then we would have 4 heads with now 5 query size each. So each head now, of course, gets a smaller query size because we basically distribute the query information among different heads. So when we again look at this idea of asking questions, we can either ask one big question, so with a 20-dimensional question space, you might say, or we could ask 4 smaller questions. And it turns out that asking these 4 smaller questions is more efficient, or is usually preferable. But of course, now we also have a 3-axis array. And again, if there was a batch axis here, that would now be a 4-axis array. Okay, but similarly, we can reshape the key and value. So key is also key.reshape into sequence length. So this still up unchanged, self.number of heads, and channels integer divide by self.number of heads. And ultimately we also have the value, which is value.reshape into sequence length self.number of heads and channels integer divide by self.number of heads. Okay, let me also add a comment and say here we will reshape to split the heads, or to split the query size among the heads. Or it was correspondingly the other sizes. So I think here I called it query size, but should also be the key size of the channels, but I think you get the point. Now we are at the point that we have these individual queries, individual keys, and individual values. And now we need to compute an attention. And now the point is, this attention vectorizes over the heads. So we, instead of asking the 4 smaller questions after one another, we will ask them in parallel. And for this, we will then get our results as saying jax.vmap over scaled dot product attention, and apply it to query, key, and value, which have these 3 axes. But again, recall the scaled dot product attention was defined for 2 axis arrays. Now we call it the 3 axis arrays. That's why we do the vmap, but we need to be careful that vmap by default vectorizes over the 0th axis, so the leftmost axis, which would be vectorizing over the sequence length, which was what we actually wanted during the projection, but now it is no longer what we want during the attention mechanism. For the attention, we want to vectorize over the attention heads. So we will say in axis is going to be -2, which means -1 would be the last axis, -2 would be the second to last axis, so that we go from the rear. And this is of course the heads axis. And of course, we also want this to be our out axis. And we say vmap over the heads, and then also produce an array where the vectorized axis is still in the middle of this 3-axis array. And ultimately, we want to concatenate again the results. So as we also see here in the mathematical description, ultimately before we project them back into the channels, we concatenate them together, because now the questions are asked, the results are in, and then we concatenate the results, and then a weight matrix makes sure that all the different results are correspondingly shuffled or mixed together. Let's call this the result, or maybe before we do this, let me add the comment here and say compute attention while vectorizing over the heads. And then the results are results dot reshape into sequence length and channels. And by doing so, the last 2 axes are basically concatenated. And let's add this, we will say concatenate the heads. And then we are almost done. Now we need this final projection, and can say out is basically self.out projection applied to the result. And again, we are in a similar situation as to before. We want the linear layer to vectorize over the sequence. So we will do jax.vmap over the out projection. And also adding the comment here, project the output, vectorizing over the sequence length. And this is then the result of our multi-head attention. Okay, this is future Felix dropping in here because the next segment of the recording unfortunately was broken. But anyway, let's continue with the coding. So in this previous block, we implemented the multi-head attention, so the main important part of the transformer architecture. And now we're going to use it to abstract one block of the transformer. Let's do that. Let's go into the next cell and instantiate a new module. Let's say class transformer block. And again, this has to subclass from equinox.module. And as the attributes here within one transformer block, we will have our multi-head attention. Let's call it MHA. which is the multi-head attention of before. Then each transformer block has a multi-layer perceptron, let's call it MLP, for which we will use a pre-built component from Equinox. So we can do equinox.neuralnetworks.mlp, and then we're going to use two layer norms, a norm 1, which is equinox.neuralnetwork.layernorm, and a norm 2, which is also equinox.neuralnetwork.layernorm. And then let's start first with the constructor. So define __init of self. And then what do we need in our transformer block? So we need to define the number of heads, which we're going to use to instantiate the multi-head attention, which is going to be an integer. We need to set the number of channels, which is also an integer. And then in the processing, as we will see later on, it is typical that the hidden layer that is within the MLP is larger than the typical channel representation of the residual stream. And so we will abstract that by using a multiplier. I just want to call this the MLP channels multiplier and set its default value to 2. And we will see that in a second. Then we need to define an activation function, which has to be a callable, and by default I want to use the relu activation function. And then for pseudo-random reproducibility, as with all the other modules, we need to provide a key, which is going to be a pseudo-random number key array. Then the first thing we do is we split our random key, because we need randomness to both instantiate the multi-head attention and the MLP. Let's split it into an MHA key and an MLP key by using JAX.random.split on the key into two subkeys. Then the instantiation of the multi-head attention is fairly straightforward. In the constructor, it only needed the 3 arguments here. So let's do that and say self.mha is going to be our multi-head attention that we just defined. We're going to set the number of heads to the number of heads, the number of channels to channels, and set the key to the MHA key. That's our multi-head attention. Then we can instantiate our MLP, so self.mlp. And as said, here we will use a pre-built component to not have to implement an MLP ourselves. So Equinox neural network.mlp. Then okay, here we go, autocomplete is here. So that requires us to define the in-size. But here we have to be careful that later on we're going to use the MLP vectorized over the sequence length. So we will have it apply on the channel axis only. As such, the in-size is just the number of channels. So in-size is channels, so is the outsize, and then I hope, unfortunately, you can't see it at the moment, but then we have the width size, which is essentially how wide the hidden layers are. And for this, we're going to use the MLP channels multiplier and multiply that with the number of channels. And since we, I think, probably have a typo, oh yeah, it's up here. And since we set it to 2, that means that the hidden representations are twice as large. Then we also need to say how many hidden layers do we want. That's done by the depth argument, and that I just want to hard code to 1. So we just have 1 hidden layer. Of course, this is a way to tune an MLP. Technically, of course, an MLP with 1 hidden layers already gives us quite a big expressiveness, but here that's of course an option for tuning. But let's just hard code it for simplicity. And then as the activation function, I will hand over the activation function, the JAX NN relu. And then similar to our weight arrays in the linear transformations that we had for the multi-head attention, we will deactivate the biases. So we will say use bias false to not use any bias in the layer transitions, and also use final bias equals false to not have a bias in the last layer of the MLP. And then as the key, we're going to use the MLP key we just set up here. So this gives us the MHA and the MLP. Then we also need to define the layer norms, or we instantiate the layer norms. So we say self.norm1, and here we go equinox.mha neural network.layer norm, and once the autocomplete pops up, it will tell us to provide the shape. So again, the axis over which we then apply the layer norm is not the sequence axis, but it's the channel or feature axis. And, or in a language context, you might also say the embedding dimension. And that one is then respectively the channels. I would just copy that line and replace norm1 with norm2 because it's the same for the second layer norm. Okay, with the instantiation done, let's go to the forward pass or the call signature. Let's take a look again at the schematic of the transformer. So essentially what we want to implement is that transformer block. So what happens first? We use our input and it goes into the multi-head attention. And then afterwards, it is added with a residual stream. So there's basically a bypass over the multi-head attention, which is added to the output of the MHA. And then we apply the layer norm, but then we have to be, again, careful that the layer norm needs to be vectorized. Then this output, well, it ignores this attention using the other part of the transformer, which we don't have here. So we basically directly go into the feed forward, which they may mean is an MLP. But here, that one is also vectorized over the sequence length. And we also have a residual stream here. And then eventually, we also have to apply a vectorized norm. Okay, let's do just that. Let's go all the way down here and go into the call method. Let me scroll down a bit. So def underscore underscore call underscore underscore, which is going to take self. And then we need an input x. And this is going to be a floating point tensor with array with the following shape. So it has the sequence length and it has the channels. And then what does it return? So it returns another floating point array with the very same shape. So sequence length by channels. Okay, so first thing we do is we say x is self.mha applied to x plus x. So for the MHA, we obviously don't have to vectorize because it is inherently built for these two axis arrays which have these sequential length. So in that sense, there's no vectorization needed. And also, of course, adding the residual stream element-wise operation, that should work fine. But then to finish the first part within there, we also need our layer norm. We would do self.norm1 applied to this MHA applied to x plus x. But that would, of course, then raise shape issues. So we will vectorize it. JAX.vmap on self.norm1. Then the second part in our transformer block, well, we again have a norm, but this time norm2, and it is applied to self.mlp applied to x plus x, again with the residual stream. But here, this MLP also needs to be vectorized because it needs to vectorize over the sequence length. So JAX.vmap applied to MLP. And then we can return x, and that essentially finishes our transformer block. And now I will hand back to Past Felix. Okay, let's go to the final ingredient before we can then assemble our entire transformer architecture, and that's the positional encoding. So let's take a look at the overall schematic again. As see here, in order to get the transformer, we will now stack our transformer blocks, but before we do that, we will apply a positional encoding. So whatever goes inside of the transformer is of a shape or is of a tensor shape with the sequence length and then the channels length. But as we discussed, this intention mechanism is permutation invariant, meaning that it does not know which values are at which position. So what we're going to do is create a matrix or a two-axis array which is of the same shape as whatever goes inside of the transformer and which will then element-wise be added to this input state and thereby implicitly encodes which position we are in the sequence and in the channel. So let's create this matrix, and for this we're also going to follow Vaswani et al. Again. I will just copy in the mathematical definition of the positional encoding we're going to use. So as said, this positional encoding is going to be two-axis array with a first index with respect to the position in the sequence and a second index with respect to the channel index. And then it computes whatever is going to be added based on whether the channel index is even or odd. If it is even, then we will use this expression using a sine. And if it is odd, we're going to use a cosine expression. It seems a bit abstract in the beginning, but we were going to implement it and then see by printing out the table and look at specific values of it. Let's add a function and call this build positional encoding table. And this takes 2 arguments. So we need a max length, which is an integer. This can, of course, be the given length of the sequence. So in our case, these 160 discretization points. But I want this to be a bit more flexible to specifically produce an encoding table, which is even longer than that. And then during the layer for positional encoding, we're going to slice up this table. But you will see this in a second. Okay, so we're going to need the maximum length, and we need the number of channels, which is also an integer. And then we need this magic number, let's call it the base, but set it to a default value of 10,000. And then what does it return? It returns a floating point array of the shape max length and num channels. Let's start by creating an empty array or with 0 values, which represents the shape of what we're going to return. So let's call this PE for the positional encodings. And this is jnp.zeros of max length and num channels. And then we're first going to define an array which has the position indices. So let's call this position, and this is jnp.arrange from 0 to max length. And if we did this command, and let's add some typing information, this would essentially create an integer array which has the length max length. Then we also need an array which represents the channel indices. So let's call this, oh sorry, that's not what I intended, but let's call it channel, and also have this an integer array, but this time with num channels. And for this we will do jnp.arrange from 0 to num channels. But since we have to handle the even and odd channels differently, I'm just going to extract the even channels for now. So let's call this the even channel. And for this, we're going to access channel at every second index. So I'm going to do this, or maybe to be verbose, to say start at 0, start at the beginning, but get me only every second index. And if I do this, this would then give me an integer array of num channels divided by 2. And then we can use this array to compute the frequency scaling. So basically this is the value in the denominator by just taking this array, dividing it by the number of channels, and then raising 10,000 to this as an exponent. So let's call this the frequency scaling, which is going to be a floating point array, which also has num channels divided by 2. And this is going to be, I'm going into the next line here. And in order to get this, I will use base raised to even channel divided by num channels. And then in order to build up the positional encoding, we need to compute both the values for the even channels and for the odd channels. Let's call this PE for even channels. And this is going to be a floating point array, which in this case should have max length and num channels divided by 2. But how do we get this? So in order to get such an array and to do it efficiently, we would need the broadcasting and vectorization capabilities of NumPy. And in order to do this, we are going to add singleton axes to these one-axis arrays. So we're going to turn this position array, which is just a single axis, but with a max len dimensional axis, into a 2-axis array with a singleton axis in the rear. And this can be done by indexing it at colon and none. With the none, we basically add another axis. And then for the num channels, we do it similarly, but here we add one in the beginning. So 1 num channels can be done by non-colon. And then correspondingly, we also need to adjust our indexing here. So we want this to be 1 and then num channels divided by 2. So here we also need a colon to keep this leading singleton axis. Here we also need a 1, but we don't need to do any manipulations here because it's an element-wise operation anyway. And then we can compute the positional encoding and just do the operation as we have it here, and internally we will automatically broadcast and vectorize the operation accordingly. So this is chain p.sign of position divided by frequency scaling, and we can compute the positional encoding on the odd channels with float array of max len and num channels divided by 2. And for this, we will just use the cosine of position divided by frequency scaling. You might now wonder, okay, why can we use frequency scaling again? It seems that frequency scaling is only valid for the even channels, but here it turns out that we want, or in the mathematical description, we compute the encoding for the odd channels by 10,000 raised to I minus 1. And this is essentially as if we were to use the frequency scaling with the even channels. So we can just repeat this. And I probably use some weird Unicode here. So let's replace that with a correct ASCII character. And now that we have basically two matrices or two axis arrays, which have in their second axis half of the components or have half of what we need in the full array, we are basically zipping them together into one another, such that we on the very first channel we get the result from the evens channel. Then at the channel thereafter we have odd channels, so we need the result from the odd channels, and so on and so forth. And for this we will just say PE is PE at, and then colon for all entries in the sequence length, and then 0 : 2 means start at 0 and every second index, and say .z, and then do PE even channels. And similarly for PE at the odd channels, so at colon 1 : 2, we will set PE odd channels. And this should be it. I hope I did not forget anything. You will see. Let's return PE. So we basically now have a function that produces this encoding table. So let's take a look at this encoding table for some sample inputs. And we can plot the two-dimensional or two-axis array as an image. So we will use plt.imshow and apply it to build positional encoding table. And here I will just use a maximum length of 300 and 100 channels. So this would now create an image which would have the, and we would basically see the position on the y-axis, but I think it's more reasonable to have position on the x-axis. So I'm just transposing the matrix here. Let's use as a color map red, blue, reverse, and set the aspect to auto. Then let's add the color bar and use an X label of position, and use a Y label, not Y scale, but a Y label of channel. Then let's execute this, and we should now see an image, hopefully. Okay, nice. Here we go. So we see some interesting patterns in here. And we now have on the x-axis these 300 potential positions, and then on the y-axis we have the corresponding channel. And how does this work now, since we add the positional encoding element-wise? Let's assume at token entry or sequence entry 50, at channel 0, let's assume that the input to the transformer was 1.8. And here, let's say, for instance, this is a dark red value, so it's 1. Then, after the positional encoding is applied, the value would be 2.8 instead of 1.8. However, if it was the token next to it that had the value 1.8, which here would get an encoding of -1, it would then be at 1.8 minus 1, which is 0.8. And with this arguably very strange looking pattern, a transformer gets the information on where a certain input is with respect to its channel and with respect to its position. With this positional encoding, we basically remove this permutation invariance. Okay, with this function, we have a construction for the positional encoding table, but I want to have the positional encoding as an Equinox layer. So let's abstract this a bit and implement a new class and call it positional encoding, which again derives from Equinox module. And then this has an encoding table as an attribute, and this is the aforementioned float with an float array with max, len, and channels. And then, of course, our constructor will take these arguments. And so basically it gets a max length, which is an integer. It gets the channels, which is an integer. And then it basically can build this encoding table according to the function. So self.encoding table is build, let's see, build positional encoding table with max, len, and channels. But now importantly, how does that work during the call signature? So let's implement the forward pass. And now, as said, we are at the beginning of a transformer. So our input is a float array with a shape of sequence length by channels, and we will return a modified array which is also of sequence length by channels. Okay, and now you might see there could be a mismatch between max length and sequence length. But here I did this a bit on purpose because to have it more general, in that during an autoregressive inference of a general transformer, not of the transformer we are using, the sequence length could grow, and you would then account for this by having an encoding table with sufficient length. But here for our problem, we wouldn't have needed that. It's a bit of overkill probably, but I guess it's okay for this educational example. So in order to only add to the given length of x, we will extract the encoding info that is relevant. So let's extract the sequence length from x's shape. So x.shape at 0 gives us the sequence length. And with the sequence length, we can then extract from the encoding table as much as encoding information as we would need. So let's call this the encoding info, which would be self.encoding table indexed up to sequence length and all channels. So here we use slicing up to sequence length to extract from our potentially longer or definitely longer encoding table the encoding information that we would need. And then essentially the application is of course fairly, sorry, that's not what I wanted, but then the application is fairly straightforward. We will just return x plus encoding info. However, if we were to do this, then during the training, we would see that the gradients produced by backpropagation would update the encoding table, which is not what we typically want. So we have to declare this variable as non-trainable. And we can easily do this by just saying that the gradients do not backpropagate into the encoding table. So in simple terms, we will use a gradient stop. So we will say encoding info is jax.lex.stop gradient of the encoding info. And as such, we avoid that this encoding table is going to be trained during the training of the transformer architecture. So let's add a comment and say avoids backpropagating through the encoding table because it should not be trainable. So it should not be trainable. Okay, we can then finally assemble the entire transformer as you would see it in this Vaswani paper by using the positional encoding and stacking our transformer layers. So let's do just that and go into a next block and implement a new class, and let's call this transformer, which again derives from Equinox module. And then our transformer, as said, consists of transformer blocks, which is a list of a transformer And then we also have our positional encoding, which is the positional encoding we just implemented. Okay, then let's define our constructor, which again takes self. Then we need to find the number of heads, which is an integer. We need to define the channels. We need to define the number of blocks that we want to have. We need this MLP channels multiplier, which I will by default again set to 2. We need to define an activation, which is a callable, and it should by default be the relu. And we have this max length, and here I will just use the default of 256. So this is the maximum length of the sequence that is supported. And then of course, as for pseudo-random reproducibility, we of course need a key. So again, a pseudo-random number key array. Then I want to start by first initializing the blocks. So let's create an empty list and then iterate through all the potential blocks. So for I in range of num blocks, we will first create the corresponding random key of this particular block. So let's call this the block key. And we could have either first split our random key into as many subkeys as we have number of blocks. But there is another cool function within JAX, which is called foldin. So JAX random.foldin, which allows us to deterministically create a new subkey by using some data augmentation. So we will again use our master key, and then we will just fold in the iterator index. And so in order to get the block key for index 0, we will just fold in the integer 0. And this allows us to get individual keys for each block, but of course have a deterministically reproducible procedure for this. So then we can say blocks.append a transformer block, which needs us to define the number of heads. So number of heads is the number of heads that we also have in this constructor. As said, throughout the processing within the transformer, the channels stay the same. So channels are channels. The MLP channels multiplier is the same as we have here in our constructor. So MLP channels multiplier. We use this activation. So activation equals activation. And here I think I have a typo. Okay, and of course we need to set the random key, and the random key is the corresponding block key. This instantiates all the corresponding blocks, and then we can also set the attribute. So self.blocks is just blocks, and self.positional encoding, pos encoding, is essentially positional encoding, and we will use max length and the number of channels. And then during the forward pass of this model, so let's implement its call function or call method, which gets handed over a floating point array with sequence length and channels, and should then produce another floating point array with sequence length and channels. It does the 2 steps. So first it will apply our positional encoding. So it will say x is self.positional encoding applied to x, and then it will iterate through all the blocks that we have. So for the block in self.blocks, we will just we will say x is block applied to x, and then we will return x. So a simple feed forward or sequential processing of our input. So if we go back to the schematic all the way in the beginning of this notebook, we see that we now basically have implemented this slice of what we want. We are now missing this lifting and projection and basically the wrapping into the physics state. And for this, I want you to recall what we had in the beginning. So where we said that a physics state consists of a leading channel axis, which is 1, and then an spatial axis, which is 160. And for the transformer, we want to consider the spatial axis as this sequence axis over which we essentially attend. And of course, the reasonable thing to do is to transpose it. So here we have a leading channel axis and then a spatial axis, and we will transpose it into a sequence axis, which will then be the 160, and a channel axis, which in the beginning will be 1. And then we can lift the channel axis into the hidden dimension, or this latent representation, for instance, using a multi-layer perceptron. And this is what we're going to do in an abstraction layer. Let's call this the transformer emulator. So let's call the transformer emulator, because so far what we have here you could use for sequence processing. Of course, here as said, we don't have any causal masking implemented, but there might also be applications for which you don't need it. So you could use this architecture for those applications. But now we're going to wrap it and turn it into an emulator architecture. And here I also want to be precise that we're now implementing it for one-dimensional states. So while I add this 1D here. So again, this is subclassing from equinox.module. And here we additionally have a lifting layer, which we will use an MLP for. We will have a transformer for which we use our handy transformer that we just implemented. And we will have a projection, which is a neural network MLP again. Let's define its constructor. So __ init of self. And then what does it take in? So it should take in the input channels, which is an integer, the output channels, which is also an integer. We need to define the hidden channels, or essentially the channels on which the transformer will operate. We need to define the number of heads, which is an integer. We need to define the number of blocks, which is an integer. And then we also have the multiplier. I think I will just copy it from here and go down there and just paste it in here, which is more or less the same as we have it up here. So then what do we have to instantiate? So we need to instantiate the lifting layer, the transformer, and the projection. So here again makes sense to split the key and not use the fold in. So let's split it into a lifting key, a transformer key, and a projection key by doing JAX.random.split the key into 3 subkeys. Then we will instantiate a lifting layer. Self.lifting is equinox.neuralnetwork.mlp, and this requires us to set the insize. And for the insize, we will use in channels, because as we had it before, we will have the MLP operate over the channel axis and then vectorize over the sequence axis or over the spatial axis. The outsize is then of course the hidden channels, because it's supposed to be lifting, so it should bring us into the hidden channels axis, not hidden channels, but hidden channels, okay. And then as the width size, I will also say hidden channels. So here it does not make sense to have this any wider, because here in that sense we just have like a lifting. I will set its depth to 2. This is also a bit of a magic number. So let's just add this here. So this is 2 hidden layers. Potentially you can do more, you can do less, but I think for these lifting and projection layers, having depth of 2 is usually sufficient. As the activation, we will use the aforementioned activation function. And here, in contrast to the MLPs we have within the transformer, I do actually want to use biases, and I also want to use a final bias. The default settings of Equinox would be that those are true, but I just want to make this a bit more verbose. And then as the key, we're going to use the lifting key. Wonderful. So this gives us our lifting. Then we can define our transformer, which is the aforementioned transformer. And then let's see, wait until this pops up. So the number of heads is the number of heads. As the channels, we are of course operating in the hidden channels. So we will set this to hidden channels. The number of blocks is the number of blocks. And as the activation, we're going to use the activation. Then we will set the MLP channels multiplier to the MLP channels multiplier. So this is just forwarding this. We will set the activation to the activation, and the max length is a bit tedious to this max length. And finally, we will need to provide the key. And as the key, we will just use the transformer key. We are only lacking the projection. So self.projection is equinox.neuralnetwork.mlp with an in size being the hidden channels and out size being the out channels. And as a width size, I will again use the hidden channels. Hidden channels. Let's scroll down a bit. And as the depth, I will again use 2. So we will again use 2 hidden layers. And activation, or I guess I can probably copy this from up here. Of course, we should be careful to change the lifting key to the projection key. And then we basically defined our projection MLP. So it's a bit tedious. I know it was a lot of typing, but essentially we now have these MLPs which allow us to lift from one channel. So essentially we will then have one channel with the advection equation to a hidden channel representation. So for instance, 20 channels, and then also project it down to 1 because we have this emulator architecture. So we need to map from the layout of a state to the layout of a state. Then let's go to the forward pass of our emulator. So implement its call signature, and let's do, this was not what I wanted. Let's do self and then the input to this. So now we finally have a different input. This is a floating point array with inputs being, let's do in channels and number of points, so number of discretization points, and it returns a floating point array of out channels, and number of points. Now we do what I just mentioned, is that we basically now transpose the axes. And this, of course, here fairly straightforward. It's a 2-axis array, it's a matrix, so transposition is clearly defined. And by doing so, we then consider the number of points, so the spatial discretization points, our sequence axis. Okay, let's write this down. So we will transpose to number of points, and in channels. And we do this, number of points is then considered the sequence length. Okay, it's fairly straightforward. We will just say x is x.transpose. And then we basically now, when we were to add the typing to this, it would be, as mentioned, num points and in channels. And then we can apply our lifting. And as we've done with most or all MLPs so far, is we will have it vectorize over the sequence length over this num points. So we will say x is jax.vmap of self.lifting applied to x. And let me also add a comment here. Vectorize over the sequence length, or by now you could also call it the number of points axis. So let's say i.e. the num points. If you were to think of it in terms of convolutions, this is essentially doing a 1-by-1 convolution. So something which does not convolve over states, but just maps channels. So what is what we do with our lifting. Then of course the logical next step is to apply the transformer on x, and then we will again vectorize over the sequence length during the projection. So x is jax.vmap of self.projection applied to x, and then ultimately we can transpose back into the input format by returning x.transpose. So we map from the physics layout to the transformer layout, lift our channels, apply the transformer, project back, and transpose back into physics layout. Let's shift enter this to have our transformer architecture. I used activation twice, so let me quickly check. So activation comes after the MLP channels multiplier. So that should hopefully work. What a lengthy implementation. I think the transformer architecture is the most sophisticated I've presented on the channel so far. But now with that one done, we can finally train it and test it, and also make it compatible with APEBench. So that's going to be the next steps. But before we can do this, it's of course wise to do a little bit of testing on the implementation. So let's instantiate it, one of our transformer emulators. So let's call this a dummy emulator just for a test, and use our transformer emulator 1D, and basically just use some simple settings. So later on, when we then have the advection equation, we will of course have one in channel, one out channel, And for simplicity, let's use maybe 24 hidden channels across 4 heads and use 5 blocks. I think the rest we can leave on the defaults and set the key to jax.random.key on 42. And let's see if the instantiation works just fine or if we get any errors. So it takes a while because there is quite some weight matrices to instantiate, but still fairly quick. So this dummy emulator, so construction worked. Let's count its parameters. And there is a useful routine in PD Equinox, which is a PD emulator suite I built as part of APEBench, which is also exported within the APEBench import. And it's just count parameters and apply it to our dummy emulator. And let's see. So under these settings, it has around 32,000 parameters. So it's like a lower end deep learning size. Let's apply it to a dummy input and do the dummy emulator and apply it to train data on 0, 0. So apply it to the 0th frame of the 0th trajectory. And hopefully that goes through. Okay, so it seems that the multi-head attention has no attribute out projection. So I guess then during the construction, I might have used a wrong name for it. So let's go all the way up. So here we have the transformer block and I called it the output projection. Yes, I think then let's use the name because it's also the name we have for the attribute. And then we just need the output projection. So let's execute all the cells again. Then we reinstantiate and let's call that one again. Okay, that seems good. Goes through. If it does meaningful things, we will see after training, but at least that is a good sign for it. Okay, let me delete this line. And then essentially what we would now do is use this training data, slice it into windows of length 2, and to then do our one-step supervised training. So this is how you would do it manually. If you're interested in how to do this, I will have a video linked up here on training an emulator for the Kuramoto-Sivashinsky equation, also with a one-step supervised learning. But since it's a bit tedious to set this up and we don't have to repeat the training pipeline, we will just use APEBench abstractions for that. But in order to make the architecture compatible with APEBench, we need to register it. And so we need to include constructor which is compatible with what APEBench expects. So for this, I will just copy in what you need here. If you need more details on this, I would recommend you to check out the APEBench documentation. But essentially, to give you a quick overview is that we will define a constructor function which works based on a configuration string and some other parameters that are handed over. And then essentially it calls the constructor of our emulator. I hope that it matches the implementation. We will see in a second. And then the important part is that we will register it as part of APEBench's components dictionary. If you had other architectures with which you want to extend APEBench, so with your fancy unit or whatever, you would also had to extend the components dictionary. Either way, so here we have that one. And with this one down, we can then start setting up an study. So we will use the study interface. For this, we need to set up a range of configurations. Let's call this the configs, which will be a list of dictionaries. And we will work in the difficulty-based scenario of advection. So that's why I do diff advection, so difficulty advection. As a network, we will have a net. I will tell you this in a second because we use some list comprehension here. As a task, we will do prediction, so basically predict the next frame and time. As training, we will do one-step supervised learning, so 1. And we will have a start seed of 0, and we will train 5 seeds at once to get our seed statistics. And then we will basically create multiple configurations based on the network architectures that we want to test. And here I just want to compare the transformer architecture with convolutional network. So I will say for net in a transformer architecture, and I want a very specific one, so I will say transformer, and then I use semicolon to distinguish all the configuration options. So here I want a transformer with 64-dimensional hidden space with 4 heads and with 4 blocks and with the ReLU activation function. And I want to compare this against a convolutional network with 34 hidden channels across 10 hidden layers, also with the ReLU activation function. And then we can basically use APEBench's convenience study. So we say APEBench.run study convenience and hand over the configurations. As the base path, I will use a folder named results, and I will instruct it to also return us some lost data frames and some sample rollouts, because we of course want to qualitatively compare both architectures. And then this convenience study should return a metric data frame, it should return a lost data frame and a sample rollout data frame, and another argument, another return, but this is not interesting. So let's execute this. And then you see the study is kicked off, and it should, in the beginning, it takes some time because it does some JIT compilations. And what I also experienced is that JIT compile of the transformer architecture takes a bit longer because we have very small grained computational parts, and the JIT compilation of a convnet or the unit is usually quicker because you have all these convolution routines. So this should also explain why the first iteration takes a bit longer, but once we have it in, the next iteration should be quicker. Okay, so we have the first iteration down, but I think it takes quite long. So now we also have the second one in. The TQDM currently counts 20 seconds per iterations. That's of course unbearably long, so you also see it would take more than 20 hours to run that study. I will stop that here, and I will save the notebook and upload it to Colab, and I will see you there in a second. Okay, welcome to Colab. So basically just uploaded the Jupyter notebook here. So it's really what we have before. If we wanted to execute this, we would notice that it would not run because we need to install Equinox and APEBench. So let's add a code cell in upfront and do just %pip install, and I don't want the AI features at the moment. So pip install Equinox and APEBench. And then of course, in order to have that run reasonable time, we will change the runtime type to the T4 GPU. So I don't have Colab Pro, so I don't have access to the more powerful GPUs, but the T4 is okay for our current needs. So let's save that. Then we can connect to the machine. Of course, I forgot a P in pip, but we are not connected anyway yet. So let's shift enter this. That should install us Equinox and APEBench. JAX and Seaborn, Matplotlib, and those stuff is already installed on a Colab instance. But let's wait for it. It takes a bit. And there we go. Now we have it installed. Then we can basically just re-execute all the cells that we also had in our local notebook running. Let's just click through it. It's more or less the same. So let's just see if the plotting also works. So training data generation takes a bit. Then we have the plots. That's what we had before. Just for reference, I quickly switched back into the VS Code session, and you would see that here we basically plotted the same data. So it's the same indices of the training data. So here we plotted this, and then on the Colab we have exactly the same result. It's not because it downloaded the data from anywhere, but it's because it has like deterministically pseudo-randomly reproduced the same initial state, which is very handy feature of JAX. And I just wanted to highlight this here because it's a fundamental feature underlying APEBench, that the data is procedurally generated and it's not downloaded, so it's very easy to use. So don't need to download gigabytes of data, but just a quick advertisement. Anyway, let's continue on running the scale dot product attention. Then we had our multi-head perception, we had the positional multi-head perception, multi-head attention and transformer block. We had the positional encoding. There we looked at it, and no, actually we have that here. It's a bit confusing because it jumps all over. So we have the transformer block, then we have our wrapped transformer emulator, then we instantiated the dummy transformer, actually with slightly different settings than what we will now use in our study. In case you're curious, we can also change this to the settings we're now going to use with 64 hidden channels and 4, and should have slightly more parameters. I guess it's around 100K. No, it's 165K, more than 5 times the number of parameters. The wrapper to APEBench, and then our collection of configs, and then eventually we can rerun it. So it should again take some time for the JIT compilation, but now we should have a significantly faster iteration counts during training. Let's see, hopefully runs. We will see. Okay, now the first iteration is through. And okay. Here we go, wonderful. And that's of course a very big difference. So the reason we saw a slower performance earlier, so it's because I ran it on my local laptop CPU, which first of all is not the most up-to-date anymore. And on top, what we also do here is we run 5 seeds batch parallel basically. So we train 5 different networks at the same time. And of course, all this parallelization only really makes sense if you have sufficient accelerators. And so here this works on the Colab GPU. Probably if you had a more beefy GPU, it would probably train in 3 to 4 minutes, but I guess that's good for us. So I will see you again once the transformer training has concluded. Okay, hi, this is a quick intermediate information. So the transformer training has finished. Took around 8 minutes here on the T4 GPU with 20 iterations per second. And meanwhile, the convolutional networks training has started. And we're looking at 45 to 50 iterations per second, maybe around half the time. And it's very interesting, as I mentioned earlier. So first of all, I mean, the transformer is a bit larger in parameter count. It has around 150,000 parameter, whereas the ConvNet has only 30,000 parameters. But this is something I experienced in general, that especially these convolution routines are so optimized. I guess some conventional wisdom is that these transformers architectures tend to scale better to larger stuff. But I would be interested to hear your opinion on that in the comment section. So I will skip again to the point when the ConvNet is trained. Okay, here we are. Training has finished, and as expected, so the ConvNet took only half the time. Let's post-process the results. So we now have 3 different data frames: the loss data frame, metric data frame, and sample rollouts. If you also want a quicker introduction into APEBench with a more simple scenario here, I will have the quick intro to APEBench linked up here. But let's just go ahead and post-process it. This is also the reason I said we want to import Seaborn earlier, because it allows us to do statistical post-processing. So for instance, if you were to look at the loss data frame, just to give you an idea of what is going on there, it basically has 1000 rows with 8 columns, and it basically stored 100 entries per run, and we in total have 10 runs. So we have 5 runs with the transformer with different seeds and 5 runs with the ConvNet. And so what we now essentially want is to plot the training loss in semi-logarithmically over the update step. So this can be done by saying sns.line plot with our loss data frame, and on X I would like to plot the update step, and on Y I would like to plot the train loss, and as the U I want to use the network, and then just set the Y scale to logarithmic. That should give us some insight into the training convergence, hopefully, once we get our plot. Perfect. So we do see the transformer in blue and the convolutional network in orange. Both, they started around, I don't know, here roughly between 10 to the -1 and 10 to the 0. So in other words, in the beginning, the average error in an MSE metric for a one-step supervised prediction is roughly 0.2 or 0.3. And then over the training, that goes down to 10 to the -6 approximately for the ConvNet, and it goes down to 3 times 10 to the -6 for the transformer. So we do go through a lot of orders of magnitude. But be advised, it's in an MSE metric, so it's actually squared. To really get a sense of that, you would have to take the square root, but both went down. Just judging based on the training loss, one could say that the ConvNet is better, but remind yourself that this is for a one-step supervised objective. So it's basically the loss for predicting one step into the future. It's not necessarily giving us, I mean, it gives us an intuition, but it does not necessarily mean that these specific networks also perform well when done under metric rollout. So basically when they have to generalize to a new test data set, and if they have to do more autoregressive steps than just one, if they have to do 100 or 200. So let's plot just that with a line plot on the metric rollout. So let's do the metric data frame, and maybe let's first take a look at the data frame such that you get a feeling for this as well. And I think it's again advertising the AI features here. let's ignore this. So basically here we now have 2000 rows with 8 columns, and as our primary metric or the default metric that is used in APEBench, we have the mean normalized root mean squared error. I think it's a very good metric because it really gives us an intuition about what is going on. It's normalized, so it's always like in a bounded range. That's quite nice. Anyway, that's plotted. So on X we want the time step, and on Y we want the mean NRMC. So X is time step, Y is mean NRMSE, and on the U we again put the architecture. Let's just execute it like this. Okay, wonderful, here we go. So it also has a reasonable Y range, so we don't have to scale this. And here we basically see how the error grows over time. And it's of course very natural. These trajectories they predict from the ground truth diverge. And now we're interested like in, first of all, how quickly they diverge. Are they like exponential divergence, which would indicate instability? Or is it like a linear or superlinear growth, which would usually indicate it's stable, but of course inaccurate, which is inevitable. And here we again see what we see some interesting behavior. In the very beginning, if you very closely looked at it, the ConvNet is below the transformer architecture. And this is also what our training loss indicates. If both architectures only had to predict one step into the future, one frame into the future, the ConvNet would actually be better. But here, this is again a bit misleading. So over time, actually, the errors that compound within the transformer are lower than what we have in the ConvNet. But on the other hand, also be fair here, the transformer has approximately 5 to 6 times the number of parameters. So in a very fair study, we would also have to adjust the ConvNet. And then I guess if you did that, you would see that they are very close on top. And of course, this is just one scenario. It's just Advection. Feel free to play around with it. I guess the good thing about APEBench is you can quickly adjust something. So for instance, if you wanted to, instead of doing Advection, you would want to do diffusion, you would say diff diffusion, or you wanted to do some burgers, so diff burgers. But I guess you get the point. Probably figure out more about this by looking at the documentation of APEBench. Okay, but this is all about quantitative rollouts. It's also interesting to look at it qualitatively. So what do they actually predict? And for this, we have the sample rollouts data frame, sample rollouts df. And, oh, I think it's just sample rollout df, not sample rollouts. And, okay, I think that takes a bit, but hopefully we get it. Yes. So essentially now this has 10 rows, and it has a sample rollout column, which is basically a 3-axis array corresponding to a sample trajectory. Of course, for memory reason, it's only one sample trajectory. Also means here sample index is 0. But of course, if you wanted to, you could also return more than that. But the problem is these sample rollouts are not yet in NumPy or JAX NumPy array. They are still in a string format. That's because the way this is saved as a CSV file. So we need to parse that first. So I'm going to add another import. I actually forgot earlier. So I'm going to import JSON, which is Python's routines to load JSON formats, and that's also conveniently usable here for nested lists. So I'm going to say sample rollout df indexed at sample rollout array is going to be sample rollout df indexed at sample rollout. So basically I'm adding a new column here, which contains an array parsed format. And here I'm just using .apply. And then I'm going to use the following lambda function, which is applied to each row. So it's going to be taking in the string representation of the trajectory. And then first it will do JSON.loads on X, which parses the string representation of the nested list. And then it returns a nested list. And a nested list can then be plugged into a NumPy or JAX NumPy constructor to construct an array. Should run fairly quickly, hopefully. Yes. And now basically I don't want to print out, because the problem is if you now force to print the data frame, that will take quite long. I don't know what the real problem is. I guess it's because these columns contain arrays which are too high dimensional. But essentially what I want to do is I want to create a facet grid using Seaborn, where in the left column, I have the prediction using the ConvNet or using the transformer. And on the right column, I have it on the other architecture. And then in the rows, I basically have the seeds. Okay, this can be nicely done by saying grid is seaborn.facet grid on the sample rollout data frame, and on the row we're going to place seed. On the column we're going to place net, and I will set the aspect ratio to 2. And then we can map to this grid the following plotting routine, grid.map, which is going to be taking lambda as well as some keywords. So we need to just match their format. And then basically what it will do is do plt.imshow on x.values0 indexed at :0 : transpose. So that's very complicated. So essentially what it will get is a list, but this list only has one entry. So we will index out this entry. Then we will essentially get our trajectory, and we want to plot it as a spatio-temporal plot. So we will take all the temporal snapshots, index out the 0th channel, take all the spatial points, and then I'm transposing it to have the time on the x-axis. So then we can do our vmin at -1, our vmax at 1. We can use red, blue, reverse color bar, and I will set the aspect to auto. And then we need to additionally define what to map over. And this is, of course, this newly created column. So that's going to be the sample rollout array. And of course, without a semicolon, that's stupid. So let's run this. Okay, wonderful. Oh, it's very large. Never mind. Okay, so essentially now on the left column, we have the transformer, and on the right column, we have the confnet. And we see basically it's all for the same initial condition. That's why the sample index is 0. It's the 0th sample trajectory from the test data set. And then we have in color, basically the state. It's bounded between -1 and 1. And as you recall, the qualitative behavior of the advection equation, maybe we can go up here, is essentially that the state moves to the right. And this is also what we see here. The state moves to the right. So it, in that case, moves to the positive values. And so this is basically seen in these characteristic lines here. And a classical problem numerical methods have with advection equation is that they introduce numerical diffusion. And this is nicely visible with the confnet. So it seemingly does predict the solution, but it smears it out. Whereas the transformer seems to do better at this. So it keeps the dark blue dark and the dark red, which is nice. And I guess this is also what contributes to the slower error growth. So overall, it seems that the transformer is a very nice suited architecture here for that problem. But arguably, as said, advection is very simple. And as a reference, maybe let's add the ground truth. So the ground truth we can get by procedurally generating this and say test data is advection scenario.get test data. Let's run this, and maybe also just print its shape. So test data.shape. Okay, cool. Now you see the test data basically is again 1 and 160, 201 time snapshots, and 30 different trajectories. And then we can do plt.imshow. We are on sample index 0, so it's the 0th trajectory. We will do test data at 0: 0: transpose. We have vmin at -1, vmax at 1, cmap is red, blue, reverse, and we will set the aspect to auto. Oh, that is a typo. I'm doing it a bit quicker now. So we have aspect auto. Oh, it's a bit harder to, that's a different aspect ratio, but never mind. I think you get the point that the ground truth is like very close to what both emulators predict, showing also that this is a very, very simple scenario. Okay, I'm back in VS Code with the results from Colab. I just downloaded the Python notebook there. And let me quickly summarize this video. So I think it was a long one. If you dig through with it, thank you very much for listening to this. And I hope you learned something along the way. So in this video, we implemented the transformer architecture with attending over space, so over spatial points for a physics state, and then embedded into this autoregressive paradigm that you commonly see when predicting spatial temporal phenomena. And it's also the one that can be benchmarked with APEBench. And you would agree, if we would have spent 30 more minutes on the training part, that would have been even longer video. So we abstracted the training, testing, and benchmarking with APEBench. So we implemented the scale dot product attention, the multi-head attention layer, the transformer blocks, and so on. And then eventually we compared its performance against the convolutional architecture. I just want to leave some remarks on the architecture to use here. So I think, unfortunately, my schematic does not work here. But what we did here is an attention mechanism over space, which I think is a good first step when translating transformers into this autoregressive paradigm. But here, a couple of remarks. First, with the advection equation, we have a problem which is hyperbolic and therefore has a local zone of influence. But with the attention mechanism, we always get a global influence. So we attend to all entries on space. This is, of course, fairly unreasonable. And if you, for instance, read the APEBench paper, you might have read that it's actually interesting to see how important it is that we match the receptive field or what we see of our physics to what actually the physics is doing to not waste parameters. So think here, maybe a transformer is a bit of an overkill, but it's definitely not a bad architecture. Of course, deep learning is also the aspect of figuring out what is actually important, and then the transformer will just learn that it only has to attend in this small region. But what you see when these kind of architectures are now used is that people start introducing some windows. So inspired by vision transformers, which also patch up the input into smaller segments and then consider those as tokens, you could very well also do this with physics states. And that's also very nice because imagine you can also have very large discretizations with 10,000 or 1 million points in 1D. And then, of course, attending over those and having this quadratic complexity that transformers inevitably get is a big disadvantage. And by patching them into smaller patches and then only attending over the patches, you can greatly reduce the cost of attention while still keeping the global connectivity. And there are also some modifications like shifted windows, where instead of having the same patches in each attention layer, but like moving them around. And speaking of patches, those also become important when you then go to two-dimensional physics states, because then the positional encoding gets a bit harder, because you then not only have a position in one axis, but you have a position in another axis as well. So there we also need some considerations, and equivalently also in 3D and in higher dimensions. But of course, this is work that is to some extent has already been done, and you can find some corresponding papers, or there are also still some open points with respect to how to do this best and whether transformers are a good choice in these physics problems, which I think so far we don't have a definite answer yet. Definitely there is some anecdotal evidence that they can be helpful and do work, and especially if we like scale it up and look at more complicated stuff. But I guess time will tell how important they are for these emulator tasks.
This channel is supported by Pasteur Labs and the Institute for Simulation Intelligence. Click the link in the video description to find out more how they merge machine learning and simulation in order to reimagine the scientific method. Also, a big thanks to all my Patreons. If you also want to support my vision of free education on advanced mathematical topics, you find the link to the Patreon page down in the video description.
Thank you so much for watching this extremely long video. I hope you learned something along the way. Please feel free to subscribe to the channel and like the video. There's more content like this on emulator and operator architectures like ResNets, FNOs, and so on. So I'm pretty sure you will find something on this. Here you will now find similar videos, and I hope to see you in one of the next videos.